and we'll introduce those guys one by one. First of all, it's the force of gravity, also known as weight. That was the very first one that we used. At first, we just treated it as the force that causes the magic acceleration for everybody. So that magic acceleration is of size g. So we basically work backwards, making sure this is consistent with Newton's second law to say, well, that must be the force. If it causes that acceleration, if you left to its own devices, that must be the force that is behind it. And the direction, of course, was downward. And that sufficed just fine through homeworks 4 and 5. And then, of course, in homework 6, we got a little bit more serious about gravity, and not just that, oh, it's that force that causes the magic acceleration for everybody, but we saw where this came from. So this right here, I guess let me leave this as capital R, lowercase r. We talked about the universal gravitational law, that just because you have mass, you belong to a club which attracts all other masses. And the amount of force will be dependent on the two masses and their separation center to center. So, of course, this thing in the dotted line was where our local gravity comes from. It's the fact that we're pulled by our particular planet with a certain mass, and it has a certain radius, and if you measure center to center, if we're standing on the surface, we're one Earth radius away from the center. And of course, downward was just for the object on the Earth itself gets pulled up. A more generic way would be, of course, to say it's attractive. Now, which one of those two forms do you use? Well, really, they're equivalent, and if someone is willing to tell you what the g value is, then the little g value, this one, then multiply it by the mass you have and you're good to go. For instance, on the surface of our planet, it's 9.8 meters per second squared. In other cases, maybe it's handed to you. Maybe on the surface of the moon, they say it's 1.7 meters per second squared. Then just multiply by the mass, you're good to go. But some problems, they don't hand you that. So you got to calculate what is the local surface acceleration, or what's the acceleration high above the surface, and then you can compute it yourself. Okay? So that was the force of gravity. We talked about the normal force. That was the force from a solid surface. How big is it? It's just enough. It varies such as to prevent motion into the surface. It's basically our ad hoc way of making sure that if there is a solid surface, then the object doesn't just go into it like it's not there. That is the only rule that you can depend on. It varies such as to prevent motion into the surface, and it is perpendicularly away from the surface. So if you don't understand that on a deep level, you start to just plug in things that aren't quite true. Sometimes n is mg, sometimes n is mg cosine theta, sometimes it's something else, sometimes it's something else. The point is just making sure that you catalog all the forces that are trying to smush the surface, and you make sure the normal force kills them all. Okay? The tension, that's the force from a rope or a string. That also varies. A rope can carry zero tension, a little tension, a lot of tension. A lot of times a rope will break if you exceed a certain tension. But if you know it's not breaking, you may be able to infer what job it is doing. Okay? The only thing that's different about the tension really is that ropes have a one-wayness to their force. They can only pull, never push. So they pull along the rope. They never push. So we saw some applications of tension problems as well. The most complicated these got were like pulley problems or hanging things like the traffic light problem from homework 4. So then to close out the initial set of stuff, we included friction. Friction, in some sense, is complicated enough that it's really, get down to it, we wouldn't include it in this course, but having the whole course have no friction whatsoever is so far from everyday life that it would be a little silly. So we've come up with some formulas that reasonably work. For instance, when you're stopped, the friction will adjust to try to keep you stopped. That's called static friction. How much can it pull to keep you from moving? Well, any amount necessary up to some maximum value after which it gives out. And the way that you calculate that maximum value is by multiplying the static frictional coefficient by the normal force, being a measure of how hard the surfaces are pushed together. So one thing that is commonly forgotten by students is that it can be anywhere in this range, as needed. Notice that just like the previous two forces are as needed, so is this. The only difference is this one has a maximum cap, and after that, it can't keep up. So if you push on something hard enough, you can smash the surface, you can crush the surface, but we usually neglect that. You can pull so hard in a string that you snap it, but we neglect that. But it would be silly here to say that you push something and you can never move it because friction will not allow you. Of course, we know at some point you can move something. So then we move over to kinetic friction, which we use a different coefficient, the kinetic friction coefficient, again multiplying by the contact force as measured by the normal force. And the direction, it's always against you. Okay? It's always trying to prevent what you're up to. So that right there basically closes out the forces that were on your first batch of material. I think that even goes beyond exam 1. The one thing that you may notice that is perhaps missing at this point, in the first 6 homeworks, we also talked about centripetal force. That does not belong on this list because that's not a real-world force. Okay? The centripetal force is another name for required force. It's an amount of force required to hold a circle. Just because you want to get that required force doesn't mean you get it. In fact, one or more of these has to be providing that. So you've had at various points, most of these forces have been the thing that helps you hold a circle. Certainly tension, we made things go in a circle with a rope. We, of course, up here, we used the universal gravitational law to hold orbits for planetary bodies. So you're able to calculate the orbital speeds and periods of planets and asteroids and forget what else, all sorts of things. So make sure you understand why centripetal force doesn't properly belong on this list, because it's not a real-world force. There are no magical circular elves whose only job is to make things go in circles. Centripetal force is just a requirement that you either meet or don't meet. You don't have to go in a circle. It's a privilege, not a right. So that may be the kind of the batch that you remember from the early part of the course. They were all kind of introduced in short order. But let me make a list of things that we've sneaked in here and there. The other force that we introduced was the spring force. That came much later. I think that was probably around homework 10. I think that even missed the second exam. The size of the force, well, if you're working in magnitudes only, the way that you get that force is by multiplying the spring constant, which is basically a measure of how stiff your particular spring is, with how far did you take the spring from equilibrium. So no spring exerts force when it's at equilibrium. It only exerts force when you take it away from there, compress or expand it. And in fact, the direction is back toward equilibrium. Sometimes that's represented by a minus sign, but if I'm splitting off the size and direction into two columns, then that would be following the pattern that I've already established. The reason why we didn't introduce that earlier is because if an object is moving while attached to a spring, that force is going to constantly change. So that does not play nice with the constant net force we generally need. And so we folded that immediately into the energy picture. And so the energy picture is more than happy to take care of this. And in fact, that spring force was used to talk about the potential energy stored in the spring. And so that's how we take care of springs. We pretty much are, anytime something is moving while attached to a spring, we use energy for that. Then finally, we talked about the force from a pressure difference. So this is homework 11. I guess I put the equation already. So this is a force from a pressure difference. So you basically have a competition between two pressures, both pushing on an area A, but they can only be one winner, and the bigger pressure wins. The force points towards the lower pressure. Overall force points towards the lower pressure because the bigger pressure wins. Now that formula in and of itself can be used, and in fact I think you did a homework problem where you had a box with a lid on it with different pressures, one on the inside, one on the outside, and you used it just like that. But this is also from where buoyant force is born. So buoyant force is really a subgroup of this. And we found that the easiest way to compute a buoyant force was by calculating the weight of fluid displaced. So basically the force from a pressure difference, well, what was that pressure difference doing? It was holding up water if it were in that spot. So the pressure difference is what supports the weight of fluid in a given place. And that's a lot more intuitive way of calculating it. And then here, if we have something that's submerged, we have a bigger pressure underneath, we have a smaller pressure above. The force points, yes, it points towards lower pressure, and that force ends up being upward. So another simpler way is say it points up. So that, I think, should take care of all the forces we talked about this semester. Am I missing any? Yeah. Right, but momentum's not a force. I'll get to that in just a second. Are there any forces that I talked about that seem to be missing? Okay, well, if I forgot one, I apologize, but centripetal force, again, is purposely not on this list for reasons that I talked about. Next thing, let's talk about momentum. Momentum was actually the recalibration of Newton's third law. So if you look back to the derivation of momentum conservation, it's basically a way to recast Newton's third law as a conservation law. Okay? So Newton's laws is really what this whole course is based on. Okay? The first law is contained in the second law. The second law can be used outright in terms of force method, or it can be recalibrated in terms of energy. And the third law basically is encoded into momentum. Okay? So the whole idea of this is if you have a bunch of things flying around, colliding in various ways, if Newton's third law is obeyed and the forces that they exert on each other are equal and opposite, the way that that manifests is that one is just given the momentum that the other one lost, but the total stays the same. So what you end up finding is when the net external force on a system is 0, the momentum of that system is conserved. So the dead giveaway to whether or not you should be using momentum is when you have more than one object. They're interacting in some way with each other, but you can reasonably expect that you can isolate them from the outside world. So I try to make this as easy for you as possible. So I try to make it kind of hit you over the head that, oh, it's a horizontal frictionless surface or some other such weird construction where you can say, yes, I believe that these things are completely isolated from the outside world, okay? In reality, things aren't quite so clean, so, but I like to think that the word collision itself is a loaded word, right? A collision implies a violent event between two things where the outside world, whatever influence they may exert, is minimal in comparison, okay? So, momentum, most generally, we had no more than two objects colliding, right? We typically had two objects colliding. That made it so the equations didn't get too out of control. And then one of the things you should definitely understand is that momentum and energy conservation are independent things. So make sure that you understand that you can have a momentum conserving event where the energy is increased, conserved, or decreased. So this is where you can refer back in your lecture notes. I did a whole list of scenarios. I think there were 4 or 5, maybe 6 of those, where I took a typical situation where you might see it, and I walked through, is energy conserved? Is mechanical energy conserved? Is momentum conserved? If so, why? If not, why not? If you understand that chart that I put up, you understand a lot. And especially on the final exam, I'm just going to say, here's a scenario, and you will have to decide which, if either or both, are conserved, okay? So that's where the deep kind of thinking is understanding when these things can be applied, okay? So make sure you can do that as well. Okay, so there we have force, energy, and momentum. That is a huge chunk of the course. The other major chunk, I think between these and then the rotational world stuff, that probably makes up about 85–90% of the course material. So let me say a few brief words about the rotational world, okay? Are there any questions before I do that? That's F12 and F21. I think I might have said it in class as the two objects, instead of being labeled 1 and 2, were A and B. So that might look more familiar. I just couldn't remember. So just ways of labeling objects. You can label them 1 and 2 or A and B. Any other questions? Yeah.
So on that chart that you mentioned in the lecture, so on some of those you told us, okay, so say a ball is dropping from a hill. So, but if we bring the Earth into the system, then the momentum is conserved.
Right.
So in a hypothetical question, should we just say right away, okay, the momentum is not conserved because it's not isolated, or should we just assume that, okay, if we bring the Earth into the system?
Well, I mean, I would have to give you the question in such a way as to make clear, do I want you to calculate something about the falling ball, or do I want you to calculate something about the ball-Earth system? So if I asked you, is the momentum of the ball conserved, you would say no. But if I asked you, is the momentum of the ball-Earth system conserved, you would say yes. So it's up to me to define the problem clearly so that what I'm asking for, especially on the multiple choice questions, I have to make clear what it is that I want of you. On the long answer questions, it's more open-ended. You know, you can choose how to define your system, but you may not want to bring the entire Earth into the system if you don't know enough about the Earth, or it wouldn't be helpful to calculate whatever you're trying to calculate. So that's where it requires a little bit of experience to know that if I brought in the Earth into my system to make it momentum conserving, that wouldn't help me with my goals, because that's bringing in some big thing that I don't know that much about, right? So for instance, you might know the mass of the Earth, but you might not know how fast is the Earth moving upward to approach the downward falling ball, right? So then you're introducing another unknown along with introducing the new object. So at some point you realize, I'm not going to do that. I'm going to just treat the ball by itself, and I'm going to do it as an energy conservation of the ball rather than a momentum of the ball-Earth system conservation. Are there any other questions? Okay, so let's talk about rotational stuff. Really, this is just the kind of bizarro parallel universe where we are analyzing everything in terms of rotation. So we have the kinematics, the description of the motion, and rather than talking about displacement, velocity, and acceleration along a straight line, we instead talk about everything in terms of angle. So angular displacement, angular velocity, angular acceleration. So this is angular kinematics. And at this point, I can remind you, why do we do that? Why do we go into angle with everything? Well, if you have an object that is spinning, it's some kind of solid object. Well, if I have a solid object like this, the different parts of the object don't have a common V anymore. Okay, so V is not something that we're, oh, this object has a V. Different parts of the object have different V's. And so that's not very helpful. And so what we realize is that all parts of the object sweep out the same angle at the same time. So then we can talk about the entire object all at once. Okay? So that's what we can say this, for instance, this spinning disk at this moment has an entire common angular speed. Okay? So that's your angular kinematics. The equations look exactly the same. Just replace everything with its rotational or angular counterpart. And I didn't even put them again on the equation sheet because it's just 5 more equations is just a lot of room to take up. So, you know, I assume you can construct them yourself. Just remember that the elephant in the room is that you don't get to go in a circle for free. So the unsung hero of making sure that your circular world stays circular is that all parts of the object somehow have the correct centripetal acceleration to hold it in that turn. For solid disks and stuff, that's easy enough to justify because there's all sorts of intermolecular forces that make sure that the disk stays together. Okay. Then we, of course, went to the rotational equivalent of F net equals ma, which was net torque equals I alpha. So everything has a rotational counterpart. So at this point, we realized that if we have an extended object, then F net equals ma really gets us as far as calculating the acceleration of the center of mass. So of course, that required a whole tangent where we talked about the center of mass. What does it represent? It's the ambassador for linear physics, or translational physics, the old stuff. And we talked about how to find it, both conceptually and with some calculation. And that is the only part of the object that is guaranteed to obey this law. If you take an extended object and you apply a net force, the acceleration of the center of mass is what you're really finding. So then we start to talk about, well, what about the rest of the object? Well, the rest of the object might angularly accelerate. And if it angularly accelerates, it's because of a net torque. So just to remind you, how do you calculate an individual torque? This is your equation. So first, you have a plus or minus sign in the front. Torque, like anything in the angular world, is a plus or minus depending on whether it's counterclockwise or clockwise. So everything is all about rotation one direction or the other. You also need to consider how much leverage does this force have, R, how far is it applied from the pivot, how much force is it, and the theta term accounts for if this force is useful or useless or somewhere in between in terms of the rotation. So for instance, in this example, you can draw this net force, looks like this. we comment that if the center of mass has to move in a straight line, then that's not rotating, that must be the pivot. And we notice that this force has a distance r away from that pivot, it has leverage. There's of course force behind it, and that force is entirely tangential to the circle, and so therefore, in this particular case, sine of 90 is 1. So our torque would be r times F. For the most part, with a few advanced problems aside, the torque has been such that it's sine of 0 or 90, and when the angle's not 0 or 90, I try to make it easy for you to identify. Remember how you get that angle? You draw the dotted line out from the pivot through the force application point, and you measure the angle. In this case, you can see it's 90. So that's how you compute a single torque. And of course, what goes into the net torque equation is the sum of